Chapter 9 is on differential equations. The first section is an introduction. So that's what we're going to do today, is introduce you to this idea of differential equations. Differential, hopefully that word looks familiar. That just means something having to do with derivatives. And you guys know from algebra what an equation is. So really all this is dealing with equations that have derivatives in them. Here's an example of one. Y prime equals 0. It's an equation, it has a derivative in it, and that's the type of thing we're going to be dealing with. Now, just like in regular algebra equations, we're going to be solving differential. Before we solve any differential equations, let's remind ourselves how we solve regular equations. So here's a good example of a regular equation. How about 2x squared equals, 5, something like this. Okay, so in a regular algebraic equation, the goal is to find x. We're looking for a number, a numeric value for x that will satisfy the equation, something we can plug in for x that will cause this equation to be true. And the way we do that is by manipulating the equation. The first thing we can do is divide both sides by 2. You learn that there's all these rules that you can follow, things that you can do to the equation to manipulate it. One of those rules is you can divide both sides by anything you want as long as you do it to both sides. Here we get 5 halves. You could also do things like take the square root of both sides. Hello! And that would leave me to a final answer, answers rather, plus or minus the square root. 5 halves. What makes differential equations different than regular equations is that you're not looking for a number. You are looking for an equation. If this is a differential equation, I am looking for y, but y isn't necessarily going to be a number. Y is going to be some function, some equation. Let's take a look at this first example. We're looking for some function whose derivative is 0. Well, let's see. We could do y equals 3. That's a very basic type of linear function. It's a horizontal function. And this one checks out because if we take the derivative of 3, we end up with 0. So we could plug this value in. We could use this equation for y as a solution for this differential equation. Y equals 5 could also be an answer. Y equals 105 is a legitimate answer. There's many different answers to this particular differential equation. There are actually an infinite number of answers for this particular equation. Pi times e is legitimate. So we have to get used to the fact that there aren't going to be just one answer. There isn't going to be just one answer typically. There's going to be a number of answers. Y equals c it's a good way to express all of those answers. Let's take a look at another differential equation. We'll keep it nice and simple for now. How about y prime equals y? Once again, we are looking to solve this differential equation. We're looking for some equation, some function, which we'll call y, that satisfies this equation. We're looking for something we can take the derivative of that won't change the function at all. Hopefully, just intuitively, you recognize that the answer for this is going to be e to the x. Why is that? Because if you take the derivative of e to the x, you end up with e to the x. You end up right back where you started. So this would be a solution. This is the equation. This is the solution. But it's not the only solution, because we could say that y is 2e to the x. 2e to the x. What is the derivative of 2e to the x? If we try to do 2e to the x and take the derivative, well, that 2 is just going to come out, and we're left with 2 multiplied by the derivative of e to the x, which is still, just gets us right back to where we started, 2e to the x. So this is also a solution. 3e to the x is also a solution, because when we take the derivative, we get 3e to the x. You could stick any number in front of here. So again, we're used to this plus c concept, but you can have multiplication by c also, and it'll achieve kind of a similar result. The derivative of c times e to the x, where c is a constant, is c times e to the x. So no matter what c is, it will satisfy the differential equation. So this is the basic setup here. We're looking for equations that satisfy a given differential equation. We're going to learn all sorts of tricks and how to do this, but this first section is really just laying down the basics. So let's take a look at maybe one or two more. C times e to the x. So there's two example problems. Let's look at a third problem. Let's try, this is example 2 on page 410. Example 2. And it says finding a particular solution. So they give us a differential equation. Y prime equals 2x over x squared plus 1. Our job is to find some function y that will satisfy this equation. We're looking for something we can take the derivative of that gives us 2x over x squared plus 1. They also give you what's called an initial condition. Here's something we know about this equation, that when we plug 0 into this equation, we get 1. This is a notation that you might not be completely familiar with here. It's the same idea as f of x. I actually like this notation. I'm surprised it doesn't come up earlier in algebra or pre-calculus or something like that. We use f of x to show what's considered the input and what's considered the output. But this notation, this y of 0, does the exact same thing. And it kind of makes more sense on an xy axis to demonstrate exactly what's the input and what's the output. Input 0, output 1. So let's try to figure out what equation will get this job done. Step 1. Differentiate both sides of the equation. Just like you can divide both sides of the equation by 2, just like you can take the square root of both sides of the equation to and it'll still maintain equality, you can integrate both sides of an equation and it will not mess up the equality. This cleans up pretty nicely, actually. The antiderivative, the integral of y prime, is just y. Now we need to find the antiderivative of 2x over x squared plus 1. And we're going to do this in terms of x here. We can just do a quick little substitution method for this problem. Substitution method is a powerful way of dealing with antiderivatives. Let's set the bottom equal to u. du then is 2x dx. We can rewrite this integral as integrating, let's see here, we've got the x squared plus 1 on the bottom, that's my u, and then we have the 2x dx right there in the original integral, so that turns out to just be du. I'm going to put a 1 right there. Now, the antiderivative of 1 over u is ln u plus c. So, after I integrate both sides of the equation, I get y equals ln of u, where u is x squared plus 1, plus c. Now, this represents an infinite number of possibilities for y. At this point, there are many options. However, if we were to graph all of these, they'd all be, I don't know what ln of x squared plus 1 looks like. Let's say it looks like this. If we graphed all of them, there's ln x squared plus 1 plus 1. Here's ln x squared plus 2. Here's ln x squared plus 1 plus negative 1, or whatever. You're going to get an infinite number of graphs. However, only one of them is going to go through the point 0, 1. Plug in a 0, get a 1. Only one of these is going to get the job done. So let's figure out what that one is. We need to be able to plug in a 0. 0 squared plus 1, and end up with a 1 So we're going to solve for C, and we will be done. Once we solve for C, we will have a equation for y that satisfies the initial differential equation. So let's do this. 1 equals ln 1 plus c. ln of 1 is 0, so we get 1 equals c. The final answer then to the differential equation is y equals ln of x squared plus 1 plus 1. There we go. So that's the solution. The solution is an equation. This is different than algebra when the solutions were numbers. Now the solutions to these equations are other equations. Okay, I'd like to work through one more example real quick on page 411, number 4, which says this. There it is. Okay, show that for any constant c, the function y equals x squared. That should be x squared if you can't see that. X squared over 3 plus c over x is the solution of the differential equation xy prime plus y equals x squared. All right, so let's talk about what this question is asking. This is like saying, all right, 2x plus 1 equals 7. Show that x equals 3 is a solution. So how would you show that x equals 3 is a solution to this algebraic equation? You would just plug it in. 2 times 3 plus 1 equals 7. It checks out. It's going to be the same sort of strategy here. They are giving us the solution, and we have to just show that it works. So let's see here. The thing we're going to do, if we know y, we can plug y in. So I'm going to rewrite this xy prime. And instead of saying plus y, I'm going to write the definition of y, x squared over 3 plus c over x equals x squared. So all I've done so far is replaced y with the equation for y, which is right there. Now, the other thing I need to do is replace this guy right here, y prime. I have to get rid of that. In order to get rid of that, in order to replace it, I need to define the derivative of y. Y was given to me. So we have to go back to our derivative rules for this. If y equals x squared over 3 plus c over x, then y prime is going to be, if we do the power rule here, 2/3 x to the first, and then this is the same thing as c, so c over x is the same thing as c times x to the negative 1. So if we apply the power rule to that, we get minus c x to the negative 2. We bump the exponent down a notch. Now let's take this y prime definition and plug it in to our xy differential equation. There we go, right there. So I'm going to rewrite this guy one more time. X times y prime, which is 2/3 x minus c x to the negative 2 plus x squared over 3 plus c over x equals x squared. From here, it's going to be a bunch of algebra. Let's distribute the x to the first power. We get 2/3 x squared. We get minus c x to the negative 1 plus x squared over 3 plus c over x is the same thing as c x to the negative 1. Does this equal x squared? It sure does. The c x's to the negative 1, that cancels out with that. We've got a common denominator here. 2/3 x squared plus 1/3 x squared is going to give us x squared. So it matches up and we're good to go. We didn't solve a differential equation right then. We only demonstrated that the answer they provided us really was an answer. And this is the type of question they're going to be looking for in sections 9.1. Okay, over and out.